let me jump into just a quick overview. And yeah, feel free to just interrupt me and ask questions. I'm going to go into presenter mode. But yeah, basics of OpenTelemetry. So we chose the word telemetry to describe the project specifically because the part of kind of the observability pipeline this project is focused on is the generation and transmission of data. So all of the different groups like Lightstep and Splunk and Amazon and Google all got together and decided it would be great if we all shared the same system for generating data. In other words, come up with kind of a common language for describing what systems are doing. And then what we do with that data, that's sort of where the innovation and competition takes place. But we don't want users to having to re-instrument all the time, or having like this kind of fractured landscape where depending on what tool you're using, that changes what kind of data your system's emitting. So that's kind of a core tenet of the project, is to sort of try to standardize that language we're using around describing systems.
Right, and I think part of what we're also kind of interested in is like it's great to use you know, the signal effects wrappers and things, but if we can do some of it with OpenTelemetry and have a little bit more of an open source approach so that we're a little more flexible down the road, then that's pretty attractive.
Yeah, and I can talk a bit about OpenTelemetry distros. I don't know a lot of the details about Splunk's distro, but ours and AWS and other people, it tends to be just a configuration layer. So in other words, when you build OpenTelemetry, it's kind of a framework. Let's actually jump into that right now. So if this green circle's like your service, to install OpenTelemetry, the part that you install is called the OpenTelemetry Sdk. That's basically the client that you would install. And that thing is a framework. So it offers a lot of plugins and lifecycle hooks. So you can add your own exporter, export in different data formats, things like that. And this is the part when people offer client distros, they tend to take the SDK and just wrap it up in some of that configuration. Because when you're configuring the SDK, like the bulk of what you're doing is configuring it to like what backend you want to talk to. And rather than make people fill in all of those details, most vendors who are using OpenTelemetry full time just want to like add a little configuration layer on top of that maybe installs like their exporter. So like Amazon wants to use the X-ray exporter by default because that's what their system uses. And if there's like a standard endpoint you're supposed to talk to, things like that. So that's how the Lightstep distro works and the AWS distro works at any rate. But it's important to note that you don't want to be accessing this this SDK directly in your code or in your application code or when you're instrumenting. This is just for configuring OpenTelemetry at the setup and also handling things like teardown at the end. When you're actually instrumenting or using OpenTelemetry, you're using a separate component called the API. In a lot of clients, the API is glued directly to the implementation, but we keep a strong separation between the API and the SDK. The reason for that is to allow frameworks and HTTP clients, you know, open source libraries that need to run in a number of different services to potentially instrument themselves natively and do that with an API that's very thin and doesn't haul in a big dependency chain. So when you access the API, you're not hauling in the whole SDK. And that ensures that the chance of like there being some kind of transitive dependency conflict lowers significantly. It also means you can potentially plug in different SDKs. So we actually have a couple. There's the framework version that I just mentioned. If you don't install an SDK, then the API comes with a no-op SDK. So if no SDK is installed, then the API calls are no-ops. We also have, like in most languages, like a test SDK, like a mock SDK that lets you just test how tracing is working in your system, things like that. In the future, for languages that bind to C++ or Rust or another implementation that might be more efficient, we're potentially looking at taking the OpenTelemetry C++ SDK and using that as an implementation for, say, Python and Node to talk to through foreign function calls. So there's a lot of benefit that we get out of having this separation. But it's worth noting because it's maybe a little more complicated than other systems you might see. So then these frameworks and your application code, they all just make calls to the API. So that's the only dependency they take on. So yeah, if you're using Splunk stuff or somebody else's, as long as you're just using the OpenTelemetry API or something that's just like maybe a high level convenience functions on top of that, then you're totally neutral. You're not gonna need to worry about vendor lock-in or anything like that. So that's I think the key distinction there.
Right. Yeah, I was I was looking a little bit at oh, there's the collector. Yeah,
Yep.
that's the thing that I was kind of looking at. Like, okay, you know, if we sort of use the signal effects libraries for right now, or maybe some of the AWS their repository or Lightstep or whatever. Then, but the big thing that like even signal effects was saying like, hey, if you want to use OTel, like all of our stuff is compatible with that, and you just make an OTel collector, and then you can do all your configuration on the collector, and that way you're a little more flexible in the future.
Oh, got it. Yeah, maybe they're talking about like their old school agents. So yeah, I think, you know, Signal Effects got acquired by Splunk, so maybe like they had some old APM products that then can talk to this. So another example, I think Datadog works similarly. But yeah, in general,
the Signal FX APM is actually like their wrappers are actually a fork of Datadog, and then they added a few other things. So yeah, I think the idea is that they're moving more towards strictly OTel, and you know, it'll obviously take some time, but that's what why I'm trying to get a little ahead of it.
Yeah, exactly. And that's sort of like the point of the collector. The collector is sort of like a Swiss Army knife, where it has a set of receivers, a set of processors, and a set of exporters. And the receivers and exporters can consume different kinds of data. So you can consume, you know, I'm pretty sure there's a Datadog receiver, there's an X-ray receiver, and then there's, you know, a Zipkin exporter and a Prometheus exporter. So it's sort of like a translator. So you can take in any common format and then produce it out any common format. And there's like a set of processors you can run in the middle. So that's also where you can do things like data scrubbing, you know, cleaning your data, adding additional attributes or details to your spans, things like that. It's also useful to move all of your configuration there. The way we recommend running OpenTelemetry is to kind of run the clients in default mode. The Lightstep launchers, that's like our distro, they actually run in this mode. We use OTLP natively, which is the OpenTelemetry protocol. So OpenTelemetry has its own protocol, and the reason for that is it combines all of these different signals into a single data stream. So you're getting system resources and tracing data and metrics, logs, you know, whatever we end up adding to OpenTelemetry as a source will all be in a single stream in OTLP. So kind of the default setup is to install the OpenTelemetry clients in kind of a default mode, and then point that at a collector, either running as a sidecar or locally. And what's helpful there is it kind of moves the configuration management out of your application service, just so if you're trying to manage your telemetry pipeline or changing where data is going or what's happening, you're doing that by just redeploying the collectors. You don't actually have to redeploy your application services. So I kind of recommend running collectors for that reason alone.
Yeah, makes sense. And you said you can on that side you do like your data scrubbing. So is that also like data anonymization and that sort of thing too?
Yeah, exactly.
Okay.
That kind of stuff. It has a processor model, so you can configure it in YAML, and it just has the configuration is a lot of like, when you see this pattern, do this thing. So you can write rules for doing data scrubbing. You can also add additional data. So like if you're running the collector locally, it can also work as an agent capturing machine metrics and things like that and adding that into your data stream. So it's kind of a useful tool. I definitely, if you're operating, if you're the person in charge of like operating the telemetry pipeline and keeping it up, having a look at the collector configurations, kind of a useful place to start. And yeah, like you said, if you're using something that doesn't speak OTLP yet, then you can just consume data from that system. So you mentioned signal effects, but also like we encounter people who are already running Zipkin, and they want to start adding OpenTelemetry to like new services, but their existing services are running, Zipkin, and they don't want to have to move everything over all at once. Mm-hmm. And by using the collector, that's a way you can kind of connect up multiple tracing systems to each other and then have all of the data coming out in one format on the other end.
Okay, interesting. Got it. Thanks.
Yeah. Cool. Oh yeah, and then I mentioned before, like OpenTelemetry doesn't have any kind of database. We're never going to ship something like a backend system. That's not really, as soon as you get into that mode, then you're kind of like picking a winner, and there's no real good way to standardize that stuff. And so we want the edge of the project just to be this telemetry pipeline, and then making sure that OpenTelemetry works well with all the existing systems that are out there. We have a spec model, I should mention, when it comes to actually designing all of this stuff and implementing it and ensuring it kind of looks similar across all the different languages. So if you go to the OpenTelemetry organization on GitHub, you'll notice there's a repo called specification, and that's kind of where we do all of the design work. So people make RFCs against that spec. We call them OTEPs. And once an OTEP gets accepted and it's been prototyped properly, then it gets written out into the spec, and then the maintainers of the different language clients implement a version of that spec. And we actually just hit 1.0 with the specification last week. 1.0 means the tracing spec is now considered stable. We have stability and long-term support guarantees associated with that. And that's basically to ensure that future versions of the clients, once they come out with 1.0 implementations, any future version of that client is going to be backwards compatible. So you'll be able to upgrade and get performance boosts and security patches and all that stuff without worrying that all of your instrumentation calls are going to break. I should note that's just the tracing portion of OpenTelemetry. Metrics and logs are still experimental. So but OpenTelemetry is kind of factored out so that those experimental components won't destabilize the stable components that we're offering. But I should just say for like production usage right now, I would focus on just OpenTelemetry tracing, and maybe follow along with the metrics work. We're going to be try to be a little more public going forwards about our metrics roadmap and what we're thinking there.
Okay, cool. Good to know.
Cool. So this is the part where I usually go over a bit about distributed tracing and just what that is and how that works. Are you familiar with distributed tracing? Sounds like you're already using it.
Yes, but not working correctly. We did a we did a POC back in like December and got like 2 services running with distributed tracing, but I needed a lot of help with it. So that's part of trying to get a little more used to all of this, just to figure out how the flow really works so that I can put it into our actual code.
Cool. Okay.
So
Well,
I'm familiar-ish with the concepts, but by all means, go through it all again for me.
Sure. Okay. Yeah, no problem. This is like pretty basic. The first thing I usually try to establish is just, what we mean by a like distributed transaction, because that's kind of the problem. And that's just, if you have a client talking to a server, let's say you're trying to upload an image and a caption for that image, like that's what the endpoint does. We all know it's like never this simple, right? Like that server's probably like a reverse proxy, talking to an auth server, talking to some local scratch disk, and then talking to an app server that's then uploading that stuff into cloud storage like S3 for the image, and then writing down like the caption and the image URL in a data service, but that thing's actually fronting a couple of services like, Redis or Memcache plus SQL. And this is pretty distributed, but at the same time, this is also like the world's most basic app. I feel like this is your basic LAMP stack app from like 20 years ago.
Right.
So it's not really like a new problem. It's just that as things have scaled up now, it's kind of gotten a little more ridiculous, to the point where there's not one good choke point where you can just go in and kind of get a handle on what the overall system is doing. And this ends up creating a lot of work when you're trying to reconstruct what these transactions are doing. If you're like me, like trying to root cause a system, usually the flow is you get some alerts, you see some metrics, like some data in aggregate, and you realize that you want to find the root cause of that. And so then you want to find the logs. But actually just whittling down your giant database of logs to just the logs that were in that particular transaction is actually a surprising amount of work. There's no like single query you can do to just get all of those logs that were in that transaction, but from all of the machines that transaction hit. That's actually a tricky thing to do with traditional logging. And one of the main use cases of adding distributed tracing to a system, people tend to think of, being able to capture latency information, and that's important. But at the core of it is you're sort of propagating a transaction ID, which we call a trace ID, through the entire distributed transaction, which basically allows you to staple that ID onto every event that occurs, which means you can index it by that ID and then just go find them all later. Likewise, since we're also looking at capturing metrics data and ensuring this metrics data is correlated with the tracing data, you want to be able to quickly go from seeing an alert and seeing like a metrics dashboard, and then being able to just go to example transactions that are generating that particular issue. So if you see like outliers occurring or something that's setting off alert, you want to be able to just get a sampling of actual transactions that are associated with that data. So being able to kind of hop back and forth, where you start with an alert, you see some data in aggregate, from there you drop in, you look at some actual traces of transactions that are occurring, that maybe gives you some insight into what might be going on. So then you pivot to doing more queries, to looking at data in aggregate, and then dropping back into looking at the individual events. It's what we're all doing already when we're operating, but having these tools kind of combined allows you to just iterate a lot quicker. You're not spending that time and energy actually collecting that data up. You're just clicking a button and moving around through your system. And I know, like, definitely once I got used to doing it that way, it like, you know, it's like once you get automated code formatting or something like that, and then you go back to a world where you don't have it, you're like, why am I spending all of this time making my tabs line up? So it's kind of a similar feeling for me when I switch to a system like this. So yeah, basically what I just said, like combining all of this stuff into a single stream of data, and then having a tool that can actually process all of this stuff can be really helpful. I should note, though, that you can still, with a collector, tee this data off into separate systems if that's what you have. So if you have one metric system, like you're running Prometheus or something like that, and then just a tracing system like Zipkin, you can use the collector to tee that data off into multiple systems. It's also a way to change from one system to another really easily.
Yeah, especially if you're like maybe changing your system and you want to use like a collector that does that translation like before you do like a cutover or whatever. Yeah.
Yeah, exactly. Yeah,
Oh.
it can help, you know, do like kind of a slow roll off. It also allows you to easily compare systems to each other. So that's a thing we see people do with this stuff is you know, just have a bake off where they tee the data off into multiple systems and then just see what those different systems do with the data. So I think it's going to make it easier in the future to make tools that are a little more bespoke and focus on maybe just doing one thing well, and then you can kind of add that tool to your tool belt. But you know, Lightstep, and I imagine, you know, Splunk and other people are doing this, but I know Lightstep, we take all of this data and combine it into like a single workflow. So we kind of presume you have all of this data, and we try to come up with workflows that leverage the fact that you have all the data in one place. So I also expect to see more of that in the future.
Do you see any use cases of this for having to deal with with like the EU data laws and everything, or in California as well, where you have like something that's going to you know, sort of your system that's been scrubbed, and you know, customer support people can help out, but then maybe it's going to somewhere else where admins have more access to that that kind of PII or anything like that?
Yeah, I mean, you can certainly use it to scrub PII. If the idea was to like not scrub it so that some people have access to it but other people don't, like one way you could do that is to chain your processors. So if you had one like one data store where you wanted it all scrubbed, and then another data store where you wanted that data to still be there, but you know, access to that data service is much more restricted. Yeah, you could do something like that by having like a tiered set of collectors. You might even be able to do it within a single collector. I believe you can make multiple pipelines. And so you could have one pipeline that scrubbed the data and sent it to one data service, another pipeline that didn't scrub it and sent it to that more secure service.
Yeah, I think it's it would be kind of interesting because of you know, certain data is supposed to be, you know, held in the EU, and like we've got, you know, data centers in EU and the AP Asia Pacific region. And so being able to like send that specific data to a different instance that lives in a different data center, I think would be super helpful and would make the security people not have to bend so much and kind of massage what we actually have.
Yeah, I think you could potentially do that.
Okay.
You could even have a look at ensuring data where if you're trying to differentiate based on, say, user region, I mean, one way to do it is like, where's the data center? But another way to do it is where is the end user? OpenTelemetry, you might have to glue this together a little bit, but OpenTelemetry is a feature called baggage, which just allows you to kind of propagate your own pieces of context. And so if one of them is like region, you could then attach that context to your traces. And again, we want to be able to combine baggage and traces better later, but for now you could write, say, a span processor that just attached this data as an attribute to every span. And then you could have your collector just have a pipeline that's sort of like, if I see, region EU, then apply this set of PII, and if I see region US, then apply this like other set of PII scrubbing. So yeah, you could probably do something like that.
Yeah, I'll look into that baggage thing a little bit.
Yeah, you'd probably have to like kind of hack it together yourself right now, just to let you know. But yeah, I think that the tools are there, and that would be actually a really interesting use case.
Okay, cool.
Yeah. Okay, so this pile of lines here is just a usual kind of trace graph. If people haven't used tracing before, they may not have seen a trace graph like this. So I like to just go over the basics because in addition to just getting the actual log events, you're also getting some high level information. Traces consist of spans, and each span represents an operation. So this tends to get graphed like this, where you have a line, each line's color coded. The color code matches like the service or the operation. And then the length of the line represents the time spent in that transaction, so the latency. And then the arrows are network calls occurring between these different operations. So it's sort of like a flame graph, an inverted flame graph. So the top span is the client, and then that's talking to the reverse proxy. The reverse proxy then talks to the auth server. Oop, I hate how this mouse does that. Reverse proxy talks to this auth server, and then talks to this scratch disk, which is the lower blue span, and then talks to the app server, which is pink span, and so on and so forth. So that gives you kind of a high level overview of kind of what's happening in parallel versus what's happening serially. And it can also help you find where the time is going. Because while it's true that the client span takes the most amount of time overall, it's spending most of that time waiting, right? And so what you're actually trying to figure out is where the work is being done. We tend to call this the critical path. So in this case, the yellow bar represents the critical path of this trace, which is all the places where work was being done that added to the overall latency of the trace. So in other words, if you wanted to make this trace so if you wanted to optimize this transaction and lower the latency, there's a bunch of places where things are waiting, and there's also some services that aren't really adding much. So if you were just looking at, say, your data service and thinking about trying to optimize that thing, the little pink one in the bottom right, or purple one, I should say, it's easy to see when you're looking at a graph like this that wouldn't really help all that much. The most you could squeeze out of optimizing that service would still just be a small fraction of the overall transaction, because most of the time in this transaction is being spent on the image uploading spans. So if you wanted to, if you wanted to reduce latency, you would have to figure out how to process images faster. And it's easy to get that kind of information at a glance when you're looking at these kinds of graphs. When people install tracing for the first time, often, and then go look at latency sensitive operations, there's often some low-hanging fruit that kind of jump out at people because, you know, things that they thought were happening in parallel, but are actually happening serial, stuff like that, just because it can be a little hard to see without a graph like this. So
yeah,
I
it's
definitely,
super helpful. And, you know, those all those times that I'll be like, oh, well, our service is slow, and developers may say, well, yeah, it's database. And then you can point to this and be like, well, that's only part of the story.
yeah, exactly. Like it's easy. Humans are terrible at attribution. Like we think we're good at it, but we're not nearly as good at it as we think we are. And both for latency and errors, I'm often so surprised about where the problem ended up actually being. Sometimes it's in an obvious spot, but the number of times it's been just something totally weird, I've lost track of.
Yeah, for sure.
Yeah. So yeah, likewise, like you want to know where the errors are coming from. So like, you know, you might start by having like a 500 be returned to the client, but you want to be able to track that back to what was the root error, like what was the thing at the bottom of the stack that created an error that then kind of bubbled back up the stack. And that's also pretty easy to see when you're looking at a trace graph like this, because it'll be the thing that's, you know, deepest in the graph that created an error. So that's another useful thing you can see with these graphs. And then last but not least, just seeing all the individual events. This is basically, you know, looking at the logs, but now the logs are actually contextualized. So one, you can find them all. So you don't have to go searching around. You just now have all of the logs automatically that were associated with this transaction. But then the logs are also grouped by operation and things like that. So when things are happening in parallel or whatever, and the logs might normally be kind of intermixed with each other, this makes it easier to sort of tease all that apart and just look at the chunk of the transaction that you care about. So that combination, to my mind, really ups the game from just having a traditional logging tool. So I like to emphasize that it's not just that you're getting this latency data, it's also that you're getting your logs into a system where they're just easier to find. And then last but not least, you want to build aggregates out of this data as well, right? Like you want dashboards, being able to track errors and latency and other things, and being able to divide that up by, you know, host or region or, you know, route or endpoint or whatever it is. And so all of these spans, in addition to having events, have attributes. So attributes are just indexes that you can add to the span. And OpenTelemetry has conventions for all of the standard attributes you would want to add. For example, for like an HTTP client, all of the things like method name and status code and stuff like that. We have standard keys and values that we use for all of that stuff, which makes all of that data a little more discoverable because you can predict what that data is going to be. And that also means that automation can start to be brought to bear. If your system knows what kind of data it's expecting, then it can actually understand and process the data a little bit better. It can recognize something's an HTTP request versus a database request and things like that. So that's another place where having all of this data in one spot and having it kind of standardized, we think will like help further automate some of these root cause workflows that you need to go through, where you're doing anomaly detection and the system can, you know, notice where, say, you've done a deploy and it notices there's divergence in latency for certain operations from one deploy to another, and it can actually like quickly start to correlate that information and just kind of tell you, hey, you know, this attribute correlates really highly. Like you're having slow like Kafka events, like your Kafka queue is backed up, and noticing that like, hey, this latency correlates highly with a particular Kafka instance. Things like that are things you can get out of a tracing system that I find are really useful.
Yeah, definitely.
Yeah, cool. Okay. Last but not least, just a little quick thing about how tracing works under the hood. You normally don't need to interact with this directly too much when you're setting up a system, because the instrumentation you install should handle the context propagation for you. But it might break occasionally. So that's it's just important to have a little bit of an image of what's going on under the hood. So the way this works in OpenTelemetry is if you got two services here and they're talking to each other, a couple of operations in each service, and then network call in the middle. The way tracing works is we have something called a context object that basically follows the flow of execution in your program. So in some languages, that might be implemented via a thread local. In JavaScript, it's a little tricky, but there's a couple of options in Node.js and Browser.js for doing this. So every language, we've figured out some form of having a context object that follows your execution and is always available to you there in the background. So rather than having to pass this information around by hand, you can just say, get me the current context object. And it's like a bag that you can put things in and take them out of. To then make that distributed, we have the propagation part, which is you have to take this context object and then serialize it on the client side and add it to your request. So if it's HTTP, the context will get serialized as HTTP headers. And then on the server side, you have a tool that's then extracting that context, deserializing it, and turning it back into a context object, which then continues to follow the flow. So this is sort of like the underpinning of OpenTelemetry, is providing this kind of context propagation system. And then we build tracing and baggage and everything else kind of on top of this same system.
Okay, cool.
Yeah. So
yeah, we did successfully get a little bit of the using the the B3 headers. And utilizing that for some of our propagation.
Yeah, that's good you mentioned that. That's actually the one thing I think people need to be aware of the most is what headers are you using to do this, because there's a couple of them out there. And so one common misconfiguration is to have like one service configured to propagate B3 and another one's configured to propagate trace context or something else, and then they don't talk to each other. But yeah, B3 is the most common one out there. OpenTelemetry, we've been involved with the W3C to actually get official tracing headers added to the spec, so that going forwards, we won't be using something, kind of like an ad hoc standard. There's actually going to be an official standard in the HTTP spec. And this work is pretty much done. These are called trace context headers. They're not super complicated. It's very similar to the B3 headers. You have a trace parent header that has a trace ID and your parent span ID. But it also includes this extra header called trace state. And the trace state includes internal details about the tracing system. And this is actually useful for gluing together multiple tracing systems. So the use case here is you have your tracing system, you're instrumented with Lightstep or whoever, you're instrumented with OpenTelemetry, I should say, but you're saying the data to Lightstep. But then your trace goes into a database. Let's say it's like a database like hosted by a cloud provider, or even like an open source database. But yeah, let's say cloud provider, where they also have their own tracing tools and tracing system. They may want to actually continue that trace and then give you data back out of their system, so that your trace isn't just the application code you're running, but also includes components of that trace when it goes inside of a database, including a database that might be managed by somebody else. So they're not going to like install your tracing system. So trace state's this extra feature that lets multiple tracers kind of take part in the same trace. And then you can glue that data back together later, whatever final data storage system you want to put it all in. So sorry, go ahead.
So for example, like we're heavy AWS shop. So we've got Elasticsearch, we've got SQS, we've got Redis. That's all, AWS managed services. So is this the way to actually get all of that trace information to go into a service that we can't install anything on?
Okay. Exactly. So, I mean, I can't speak for AWS, but, I presume big providers will find this interesting at some point. If the way that would work is by having these systems all recognize this same tracing header, then you'll be able to have your application trace go into that data provider, and then they're using whatever system they're using to do tracing internally, and then they store their chunk of the trace somewhere, or fire hose it back to you in some way. So that'll be like, I think something coming maybe in the next year or so. I would expect this to show up. We've seen examples of this in the past. For example, MongoDB did a spike of this a while back, and showed that you could get traces that included all of like the MongoDB internals, all of the sharding and everything else. So that was pretty cool. But this would also let it be systems that you weren't running. Like, so yeah, if it's a hosted Elasticsearch instance, for example, this would be a way to get that tracing data back into Lightstep or Splunk or whatever.
So I guess maybe I'll have to check out the AWS Hotel distro and see if they have this already.
Yeah, well, they don't have it yet.
Okay.
But I should emphasize it's not something that like the distro would matter about. Like AWS has a distro for one, so they can offer support, right? Like if you want to contact AWS support and get help running your collector, their request is you run their distribution of the collector, because that only has like a subset of plugins that they've vetted and feel comfortable supporting. So
okay, got it.
So, but yeah, in the future, like potentially some of those data services may actually accept W3C headers or something to that nature, so that you could actually connect up an even longer trace, which is kind of a thing you can't totally do right now. Like you can sort of funnel X-ray data out of your system, but you can't glue that together easily with the application part of your trace today.
Great. Okay, that makes sense.
Yeah, so I'm excited to see this happen. I predict this within a year, somebody's gonna announce something like this.
Okay.
The other set of headers we're working on are these baggage headers, which are, I think I mentioned baggage before, but this is, once you have this context propagation system in place, you can potentially use this for lots of things. And so baggage is just sort of a generic dictionary that you can pass through your distributed system. And I predict people, so one use case I could see people using this for is A/B testing, right? If you're A/B testing a distributed system, parts of that system, 3 layers now, need to know, are they on the A path or are they on the B path? That can be a little tricky to set up today. Like you might need to run multiple instances of the service and do it at the routing layer or something like that. But if you can actually just pass a piece of baggage around that says, B path or A path, then every service can switch on that and know what to do. So I think people will start building cool systems beyond just observability once baggage kind of gets out there and people realize like the potential of having it.
Gotcha. Cool. I will say, since I'm the only person here, I do have a thing at 1 that I have to go to, and I know I've been asking questions, so we're going a little over. So just seeing what you wanted to do there, because I see on your sheet that it's actually supposed to go till 12:15. I thought it was supposed to be over at 12.
Oh, okay, so you've got a hard stop in 8 minutes.
Yeah.
Sure thing. Well, we can just switch to kind of looking at some code. This was the originally like the Node.js kind of Express workshop. If that's code you want to look at, we can have a look there.
Yeah, that's great for me.
Yeah, so I'll just show you where this this stuff lives. OpenTelemetry, it's a little bit of a moving target till the 1.0 clients come out. So I do try to keep these up to date, but they do kind of go out of date. But that'll change in a couple of weeks once everything stabilizes. But I've got 4 repos right now that just kind of have basics. And so the node basics is one of them. And this shows you just a bit about the setup and like how to use the API. So I won't actually run the examples because we don't have a lot of time, but I'll just kind of walk you through my recommended setup here. One thing to note is that OpenTelemetry can automatically install instrumentation. So for example, here's an Express server, and the actual Express application will get instrumented automatically once you install OpenTelemetry and the OpenTelemetry plugins. So that's pretty easy. You just install OpenTelemetry and the plugins, and if they're available, they'll auto detect whether or not the service, the library they're supposed to bind to is available, and then run. So that's good to know. And then you can add your own tracing code into your app itself. And if there's no OpenTelemetry running, this is all no ops. But this API is actually going to change a little bit, just to let you know. So if you go look at Node.js right now, I think it's in a little bit of flux, but the final result will be basically the same thing. At any given point, you can ask for the current span, and getting you the current span back. So if you're within an Express handler here, the current span will be the span that the Express instrumentation created. So this is like your server-side span, so your controller span. And so you can just grab that span and add additional attributes to it. It'll already be decorated with all of the basics from that are available at the Express level. So all of that HTTP information and route information. But if you have like application specific attributes, like project IDs or whatever, this is how you add them. So you just call get current span and then set an attribute on it. Likewise, you can use this for logging to your tracing system, and that's just called events. So you say add event. It's really basic. It's just the log message, and then you can attach a dictionary of attributes to it. And the one other basic piece that I recommend knowing about is recording exceptions and setting a status to error. This is cleaned up now. We just have one extra status code called error. But basically, all record exception does is it takes an exception and formats it as an event properly. So this is just a convenience method to ensure all of your exceptions are formatted properly. And if you actually want a span to be marked as an error, and so saying this whole operation failed, and I want this to count against my error budget or create an alert or anything like that, that's done by setting the status of the span to error. So this in the future, this will just be like, status code error. Okay. We used to have a bunch of status codes that we inherited from gRPC, but that was too complicated, so we just got rid of them. And so that's actually just, I would say the basics is just mostly what you need to do is just make sure this instrumentation is installed, and then take those existing spans and decorate them with attributes, events, and exceptions. If you have an uncaught exception, that'll automatically set the span to an error. But if you want to manage this yourself, that's how you do it.
Okay.
Yeah. So one other thing you might want to do is create your own child spans. So if you have a sub operation that you want to record, you can do that. Like get the latency and just have it broken out. You can create a child span. I don't really recommend creating lots of child spans. Some people think you should like wrap every function in a span, but that's not actually helpful. So I recommend being just kind of selective and very coarse graining these things. And if you do need to make child spans, I also recommend trying to not pepper it in your application code, but find a more like centralized place to do it. So I recommend like putting this stuff kind of like internal to an object or whatever manager you have. But when you do go to write that instrumentation, this is what it looks like. The first thing you need is a tracer. So making tracers doesn't have any overhead. All it does is gives you a name so that you know where the spans you're making originate from. So when you make a tracer, the convention is to name it after the package that it's in. So you just make one tracer per package and name it after that package. And that ensures all of the data that's emitted out of that tracer will get linked back here, so you can see where it came from. So once you have a tracer, all you have to do is call start span. Start span can take a bunch of attributes, but by default, if there is a current span, it'll bind to that span as a child span. So it'll join the trace graph as a child of whatever the current span is. Once you have that child span, you can then set that span to current. So there might be some cases where you want to manually pass a span around, but mostly you want to use this get current span convenience, so you don't have to do that. And to do that, you just create a closure. So you just say with span, and then within this closure, get current span will now return this child span. I should note you still have to end that span somewhere. So when you end the span, that's how you record the latency. And this is the one big gotcha is if you fail to end a span, you're going to create a leak, which is the other reason why I recommend kind of centralizing this kind of code rather than just copy pasting it all around your application code, because you might end up creating some situation where you don't end the span.
Good to know.
Yeah. And of course, there's like, it's easy enough to make like a helper method that, automatically ends the span, like, at the end of that function. But in this example, this is sort of a chain of things, right? So within here, we're setting a timeout, et cetera. And so that's why it's kind of a separate method. But it's easy enough to wrap this stuff up in like convenience methods if you have a pattern that you're using a lot, which is like what I recommend. Like if you have a lot of standard attributes that you want to set on your spans, I recommend just creating a helper function to do that, or making it a piece of middleware, for example, that automatically does it.